Hello, welcome back. In this video, we're going to go through another application of differentiation. It's called the Rolle's theorem. So the given functions are 3 minus the absolute value of x minus 3 over the closed interval 0 and 6. And the second function is the trig function on the interval pi over 2 and 7 pi over 6. So at this moment, I want to step back and remind you the Rolle's theorem. The Rolle's theorem states that if you have a continuous function on the closed interval a and b, and differentiable function on the open interval a and b, and if the function values are the same at the end points of the interval, so in other words, f of a equals f of b, then it's guaranteed that there exists at least one number c in the open interval a and b such that the derivative of the function is 0. And the meaning of that is if we find a line connecting these 2 points, which is going to be the secant line. So the secant line is going to have a 0 slope. The secant line is in fact a horizontal line. So to sum up, if you have a horizontal secant line connecting the points f of a and f of b, then it's guaranteed that you're going to have one point somewhere in between a where the tangent line is going to be horizontal. So at this moment, we want to check if the conditions of the theorem are satisfied. Well, first of all, we want f to be continuous on the closed interval 0 and 6. But this is an absolute value function. And whenever you see an absolute value function, what that means is the function is piecewise defined. So I can write the function description based on the absolute value function. Okay? So in other words, the inside of the absolute value, if that is positive or non-negative in particular, then the function value is going to be 3 minus x minus 3, since x minus 3 is positive. Because the role of the absolute value is to make the inside positive, but it's already positive inside. So the function value is going to be this piece. So this piece is going to be exactly 3 minus x minus 3. If x minus 3 turns out to be non-positive, then inside of the absolute value is negative. But the absolute value's job is to make inside positive, so then this piece is going to be minus x minus 3. Okay? So minus x minus 3 is going to be positive in that case. You simplify the top and the bottom piece and rewrite the inequalities here. So you have x greater than or equal to 3. And in the second piece, x is less than or equal to 3. And then this piece turns out to be 6 minus x. And this one turns out to be just x. And for me to put equality to both pieces here, I should check the continuity at x equals 3. So for x equals 3, this function is in fact takes the value of, on the left takes the value of 3, on the right, and it also takes the value of 3. So if you look at the limit as x approaches 3 from the left or the right, the function value is exactly 3, so then I have the right to put the equality sign here. In other words, at the junction point, f is continuous. So that's good news. So here is the first conclusion. F is continuous on the closed interval 0, 6, because each piece is continuous, and junction point, the limit values are exactly the same. So, and that is essentially equal to the function value. So f is continuous on 0, 6. And let's check the second property, which is the differentiability on the open interval 0 and 6. While staring at each piece here, f is differentiable for each piece if we are not considering the junction point 3. But at the junction point 3, there could be a problem. So let's sort of like investigate that. And recall from the previous chapter that we check for differentiability at the junction point by looking at the right and the left limits for these quotients. But if you look at the first one, you're approaching 3 from the right. I'm going to use the right piece for f. So let me just recall that the right piece is 6 minus x. And here the left piece is just x, okay? And f3, we just found that to be 3. And this is a good exercise to calculate those limits for these expressions. And turns out that in one case, we get -1, and in the other case, we get +1. So the unfortunate news here is that f is not differentiable at the interior point x equals 3. So what that means is one of the conditions of the Rolle's theorem fail to hold true, because 3 is an interior point, and we want f to be differentiable for all x's, for all interior x points of the interval 0, 6. So what that means is that we cannot apply the Rolle's theorem. We can't get the conclusion of the Rolle's theorem. But we can still check if there's any point for which f prime is 0. All right, now let's look at the graphical outlook of the function 3 minus the absolute value of x minus 3 on the interval 0 and 6 here. Okay, so as you see at the point 3, there is a corner or cusp where the f prime is not defined. We still have the function values to be the same at the endpoints, which was another condition in the Rolle's theorem. So if you look at the secant line here connecting these 2 points, it is just a horizontal line. But as you see in the graph, there is no horizontal tangent line because the tangent line here doesn't exist, right? Because on the left, it's this tangent line. On the right, it's this tangent line. So at x equals 3, f doesn't have any tangent line. And there's nowhere in this interval that you have a flat or horizontal tangent line. So for this particular case, we weren't able to apply the Rolle's theorem. And in fact, from the graph of the function, we can also verify that there is no flat tangent line in the interval 0 and 6. All right, this is the end of the video. Thanks for watching. I'll see you in another video. Bye.